This is part 1 of Chapter 1, Section 1, Describing and Measuring Motion. This section only talks about speed. It's 3 o'clock and school is over. You hurry out of class to enjoy the bright afternoon. A light breeze is blowing. A few clouds are lazily drifting across the sky, and colorful leaves float down from the trees. 2 birds fly playfully overhead. A bunch of frisky squirrels chase one another up a tree. You spend a few minutes with some friends who are kicking a ball around, then you head home. Does anything strike you about this afternoon scene? It is filled with all kinds of motion: blowing, drifting, fluttering, flying, and chasing. There are simple motions and more complicated motions. Motions that are over in a moment, and motions that continue all afternoon. How else can you describe all of these examples of motion? There's actually a great deal to understand about how and why all these things move as they do. In this section, you will learn how scientists describe and measure motion. Recognizing motion. Deciding if an object is in motion isn't as easy as it sounds. For example, you are probably sitting as you read this paragraph. Are you moving? Other than your eyes blinking and your chest moving up and down, you would probably say that you and this book are not moving. An object is in motion when its distance from another object is changing. Since the distance between you and this book is not changing, you conclude that neither you nor the book is moving. At the same time that you think you are sitting still, you are actually moving about 30 kilometers every second. At that speed, you could travel from New York City to Los Angeles in about 2 minutes. You are moving because you are on planet Earth, which is orbiting the sun. Earth moves about 30 kilometers every second, so you and everything else on Earth are moving at that speed as well. Whether an object is moving or not depends on your point of view. If you compare the books on a desk to the floor beneath them, they are not moving. But if you compare them to the sun, the books are moving quite rapidly. Earth and the sun are different reference points. A reference point is a place or object used for a comparison to determine if something is in motion. An object is in motion if it changes position relative to a reference point. You assume that the reference point is stationary or not moving. If you have ever been on a slow-moving train, you know that you may not be able to tell the train is moving unless you look out the window. A nearby building is a good reference point, and a glance at it will tell you if you and the train are moving. But it is important to choose your reference point carefully. Have you ever been in a school bus stopped right next to another school bus? Suddenly, you think your bus is moving backwards. When you look out the window on the other side, you find that your bus isn't moving at all. Actually, the other bus is moving forward. Your bus seemed to be moving backwards because you used the other bus as a reference point. You assumed your reference point was stationary, but in fact, your reference point, the other bus, was really moving. Describing distance. To describe motion further, you will need to use units of measurement. Whether you realize it or not, you use units or standard quantities all the time. You might, for example, measure 2 cups of milk for a recipe, swim 100 yards after school, or buy 3 pounds of fruit at the store. Cups, yards, and pounds are all units. Scientists all over the world use the same system of units so that they can communicate information clearly. The system of measurement is called the International System of Units, or in French, Système International. Sorry, I am not a very good French speaker. Abbreviated SI. The SI system is based on the number 10. This makes calculations with systems relatively easy. The basic SI unit of length is the meter. A meter is a little longer than a yard. The Eiffel Tower in figure 3 is measured in meters. To measure the length of an object smaller than a meter, scientists use the metric unit called the centimeter. The prefix centi means 100th. A centimeter is 100th of a meter, so there are 100 centimeters in a meter. The beautiful butterfly in figure 3 is measured in centimeters. For even smaller lengths, the millimeter is used. The prefix milli means 1,000th. So there are 1,000 millimeters in a meter. In the international system, large objects or long distances are measured in kilometers. The prefix kilo means 1,000. There are 1,000 meters in a kilometer. SI units are also used to describe quantities other than length. You can find more information about SI units in the Skills Handbook on page 204 of this textbook. Other examples of SI units that we have typically used, we use our mass to find in grams, and we use our volume in milliliters or liters. Calculating speed. Scientists use SI units to describe the distance of an object travels. A car, for example, might travel 90 kilometers. An ant might travel 2 centimeters. If you know the distance an object travels in a certain amount of time, you know the speed of an object. To be more exact, the speed of an object is the distance the object travels in 1 unit of time. Speed is a type of rate. A rate tells you the amount of something that occurs or changes in 1 unit of time. To calculate the speed of an object, divide the distance the object travels by the amount of time it takes to travel that distance. This relationship can be written as follows. Speed equals distance divided by time, or speed equals distance over time. Speed measurements consist of a unit of distance divided by a unit of time. If you measure distance in meters and time in seconds, you express speed in meters per second. The slash is read as per. If you measure distance in kilometers and time in hours, you express speed in kilometers per hour. If a car travels 90 kilometers in 1 hour, the car is traveling at a speed of 90 kilometers per hour. An ant that moves 2 centimeters in 1 second is moving at a speed of 2 centimeters per second, or 2 centimeters over per second. The ant is much slower than the car. Constant speed. A ship traveling across the ocean may move at the same speed for several hours, or a horse cantering across a field may keep a steady pace for several minutes. If so, the ship and the horse are traveling at constant speeds. If the speed of an object does not change, the object is traveling at a constant speed. When an object travels at a constant speed, you know that its speed is the same at all times during its motion. If you know the distance an object travels in a given amount of time, you can use the formula for speed to calculate the object's constant speed. Suppose, for example, that the horse in figure 4 on the previous page is moving at a constant speed. Find the horse's speed if its canter is 21 meters in 3 seconds. Divide the distance traveled, 21 meters, by the time, 3 seconds, to find the horse's speed. So in order to find the speed, we took 21 meters and divided that by 3 seconds to get our unit rate and our speed. That is 7 meters per second. The horse's speed is 7 meters per second, or 7 meters per second. Average speed. Most objects do not move at a constant speed for very long. The cyclists in figure 5, for example, change their speeds many times during the race. They might glide along on ground level, move more slowly as they climb up steep inclines, and dash down hills. Occasionally, they stop to fix a tire. Unlike the horse described earlier, you cannot use any one speed to describe the motion of the cyclist at every point during the cyclist race. You can, however, find the average speed of a cyclist throughout the entire race. To find the average speed, divide the total distance traveled by the total time. Suppose a cyclist travels 32 kilometers during the first 2 hours of riding and 13 kilometers during the next hour. The average speed of the cyclist during this trip is the total distance divided by the total time. So we took the total distance, adding 32 kilometers from the first part and 13 kilometers from the second part. And then we found our total time by adding 2 hours from the first part and 1 hour from the second part. Then we took our total distance, 45 kilometers, and divided that by our total time, 3 hours. When we divide that out, we get 15 kilometers per hour. The average speed of the cyclist is 15 kilometers per hour.